Hi, I am Deepan. So I will be talking about nearly optimal fault tolerant distance oracle, and this is a joint work with my PhD supervisor Manoj Gupta in IIT Gandhinagar. So let us discuss about the motivation of the problem. So as many of you are aware, graph theory are often used to represent some real life networks, and by real life networks I mean networks between some places and connections between them. So vertices in graphs can represent the places, and edges represents the connection between them, and the weights of those edges like s to u costs 1 unit and then s to v costs 2 unit. You can assume it as the distance. So if you want to go from s to u, use the distance, use the connection from s to u, then the distance traveled is 1 unit, and then s to v distance traveled is 2 unit, and so on. And so in this way you can get the shortest distance between any 2 points. So if you want, suppose you want to go from s to t, then the shortest distance will be, you will go from s to u and then u to t. Now, as we are representing some real life networks, and real life networks are often, there are often conflicts in some real life networks. So there may be some conflict due to which you may want to avoid some certain edges. So suppose you want to avoid this edge s and u, s to u, the connection between s and u. So in that case, the shortest path will get changed, and the new shortest path will be s to p and then p to u and then u to t. So these new shortest paths are represented by this notation, which is s to t after avoiding su edge, and the length of it is modulus of the value s to t after avoiding su. So these faults will keep changing. So at a certain point of time, you may want to avoid certain edges. And so after each fault, you may need to recalculate the shortest distances. And to avoid this kind of scenario, what we study is F fault tolerant distance oracle. So in a fault tolerant distance oracle, you are given as an input, you are given some undirected graphs. So we are talking about undirected graphs here. You may be given some directed graphs also. The graphs we study here are undirected graphs, undirected, and the graphs may be or may not be weighted. So undirected weighted graphs. And then you do some pre-processing and store some collection of data structures. So this collection of data structures are known as F fault tolerant distance oracle. And so this oracles or the collection of data structures can handle certain type of queries. So you query this oracle that I want to go from source S to target T after avoiding the set of edges F. So this set of edges, so we are only talking about the conflicts which are on edges. So the faults are on edges only, and small f is the highest number of faults it can tolerate. A particular distance oracle can tolerate. So you want to give a particular query to the oracle, and it will take, this oracle will take some query time, and it will answer to your distance query, that going from S to T after avoiding the fault set F will take you this much distance. And also our oracle is path reporting, so it will also report you the path. So here the main three parameters are pre-processing time, the time you require for pre-process, space, the storage you need, and the query time is the time you require for answering some query. So here we study our oracle mainly based on two parameters, which are space and query time. So let's see some of the previous results. So if you see for any varying number of edges, for any varying number of faults, so for any general number of faults, if many faults, the DR22 paper, if you fix a particular F, DR22 paper takes the query time of constant time, but the space required here is big O n to the power 4. Here in our result we take space big O tilde n square. So tilde hides some polylog factor. So there is some polylog factor after n square. But for a fixed f, the query time we require is polylog factor more than the query time taken by DR22 paper. But the space requirement is lower than them, significantly lower than them. And also, the KS23 paper takes only polylog factor less space than us, but the query time required for particular F. So if you fix some particular F, then the query time required for KS23 paper is also big O tilde n. So that's why our oracle is nearly optimal, because it is optimal with polylog n optimal up to polylog n factor for both space and query time. So before discussing about what we do in fault-tolerant distance oracles, let us discuss a tool from literature, which is known as maximizer. So maximizer DST-C1-C2 maximizes the distance from S to T depending on some conditions which are mandated by C1 and C2. So these conditions will be mandated by C1 and C2, and depending on those conditions, it will maximize the distance from ST. So this will store some maximizing set. So depending on how many number of faults we want to create, we want to tolerate at a particular point of time, we will have the size of F. So for example, if you want to tolerate 2 faults, then F star will contain two edges, which maximizes the distance from S to T. Suppose F star is, so here it stores the maximizer, we will store the fault set and the path after avoiding that particular fault set. So F star and P star is the path after avoiding particular fault set. So suppose there is another set of edges. So there may be many set of edges which satisfy the conditions on conditions given by C1 and C2, and let F be another set of edges which satisfies the condition, and the path P is the path from S to T after avoiding F. So there was a previous result in literature which says that either at least one edge of F star lies on P, or it does not. And if it does not, then it will be P is equals to P star. That is, if no red edge is on the path P, in that case we will have P is equals to P star. So in this case, we know the path. So what is the use of this maximizer? So suppose we want to find some S to T distance avoiding some fault F, and we don't know what the path is. Now, if we have the condition C1 and if we find some suitable condition C1 and C2, which is satisfied by F, and depending on that condition, we get the particular F star and the path P star, then we know that either F star contains one edge on F. So either F star will give us one edge on the path P, which we are trying to find, or if it does not, then we will have P is equals to P star. So this will help us. So this particular maximizer tool will help us in this way. Now, now let us discuss. Now let us use these maximizers for single faults. So suppose we have to find the path from S to T after avoiding the single fault AB, and in that case, we call that maximizer. We call this maximizer DST D1 D2. If we call this maximizer DST D1 D2, where D1 is the distance from S to A and D2 is the distance from T to B, with the condition that the fault there should be only one fault, and the fault must be at a distance D1 from S and D2 from T. Now this fault we require will maximize the distance from S to T. That's why this fault should be, the maximizing fault should be on ST path itself, because if it is not on the ST path itself, then shortest ST path is undisturbed. So that cannot maximize the distance from S to T. So this maximizing fault should be on ST path itself. Now on ST path at distance D1 from S and D2 from T, there is exactly one particular edge, and that's why it will just return the path itself. So this is easy if we use maximizers this way for a single fault. But the problem here is there can be S can take n many values, T, D1, D2, everything can take n many values. So that's why this will need big O n to the power 4 many maximizers, and we don't want to take that much of space. So for all maximizers, to store all the maximizers, we will at least need constant number of space. So that's why we cannot do that. So this big O n to the power 4 many maximizers is not the plan actually, but we will somehow use maximizers. So our plan is to somehow use maximizers and get big O tilde n square space for fixed size of f. So for that, what can we do is we store dst 2 to the power I 2 to the power j. Here d1 and d2 can vary from 2 to the power I from vary as 2 to the power I and power of 2. So this can be so 2 to the power I. So d1 can have log n many possibilities, and d2 also can have 2 to the power j. So that is log n many possibilities again here, such that the distance is the fault E star should be at least at a distance 2 to the power I from S and 2 to the power j from T. So these maximizers will be, these many maximizers will be at most big O tilde n square many maximizers. And so before we use these maximizers, let us discuss a tool which we have discovered, which is jump sequence using a particular vertex U. So let R be a path from S to T after avoiding some fault set F prime, and U be a vertex of F which is not on F prime. So jump sequence RST using U is a sequence of vertex on the path itself, RST. So how do we get the path? How do we get the sequence? How do we get from one vertex to another vertex? Is xi is the first vertex from RST from xi minus 1 after jump of this length. So what is this length? Xi minus 1 to u after avoiding f base 2. So what is this? So suppose xi minus 1 to u after avoiding f length is somewhere between 2 to the power L and less than 2 to the power L plus 1. In that case, base 2 value will be 2 to the power L. So base 2 value of any particular number is the highest power of 2 below it. So what we do is from xi minus 1, we measure this distance xi minus 1 to u avoiding f base 2, and we jump in this distance through R, and we get the first vertex on R in this distance, we get it as xi. And so this way we will just take jumps in RST using U. And so from xi, we will again measure this distance and jump on. So this jump RST is advancing along RST in distances xi, U, avoiding f base 2 and so on. But how many jumps will there be? For that, let us define jump length sequence. Jump length sequence is nothing but the length of those jumps, length of the jumps in the jump sequence. So, and using that definition, jump length sequence, what we say that in the jump sequence itself, there will be a vertex xj such that the jump length sequence decreases by a factor of 2 after every 4 jump till xj. So that is, if the first jump is at most, the first jump can be at most n, and then after 4 many jumps, the jump will be at most n by 2, and then after 8 many jumps, it will be n by 2 square, and so it can decrease at most log n many times this way. So after 4 log n many times, it cannot again decrease. So xj cannot decrease further, because after log n many times, it will be 1, at most 1. So that's why if it decreases by log n many times, by log n many times, then it will be at most 1, and then it cannot further decrease. And then what we say is we can assume that u is not on xj. Anyway, if u is on xj point itself, so u is the vertex xj itself, then we just jump to the next vertex. So at any point of time, we can, if the path is not exhausted, till the path is not exhausted, then we can jump on the next vertex if jump length is not something like 1 or 0 exactly. So what we can say is after xj, the sequence increases by a factor of 2 after at most every 4 jumps. So after xj till xj plus 5, it will be greater than equal to 2, and then it will be greater than equal to 2 square, and log n many such attempts log n many times, it will be at most n. And after that, we will not be able to find a vertex in the jump sequence. So after at most 8 log n many times, it will be greater than equal to m. greater than equal to n, that is the number of vertices, and from xk, if you try to jump, you will jump off that thing. So that's why in a jump sequence using U, there can be at most 8 log n many jumps. So let's now get back to the problem, which is we want to find S2 path from S to T after avoiding E, and we will be using jump sequence here. So what we do is we find the jump sequence jump RST using A and jump RTS using B. So if the jump sequence starts from T, it is say jump RTS and using A and using B. So these green vertices are jump RST using A and blue vertices are jump RTS using B. And so recall that we have stored dst2 to the power I to the power j for all I and j and for all st belongs to Vg. And so for each pair of x, for each pair from for each pair x and y from jump rst and jump rts, we look at this particular value e star xy e star. And what we claim that there is some particular xy pair for which the distance we wanted to find or the path we wanted to find st avoiding e will be exactly s to x and then x to y avoiding e star, which we have stored in that maximizer, and yt. So yt is the shortest distance. We can also store that because we can anyway store all the BFS trees, and that will only take n square many space. So this will give us our path we want to find, right? So there is some particular xy. I am not getting into proof of this thing, but how do we use? So we know that there is some particular xy for which it is satisfied, and to know which xy can be, we can just check whether xy avoiding E star contains E or not. So we can get xy avoiding E star from the maximizer itself, and then we can just check it xy avoiding E star distance is equals to x E star plus E star plus the weight of E star plus the distance of y to E star distance. So if we can just check this inequality, then we can say that we can say whether E is lying on xy avoiding E star or not. And if xy avoiding E star does not contain E, then it is a candidate to become such particular x and y pair. And so we take all those pairs and take the minimum of all those distances, and the minimum of those distances will be exactly equal to st avoiding E. And the distance from x to E star, so from a particular vertex to a particular edge, we define as minimum of the endpoint, minimum of the distances of the endpoints of the edges of the edge. So that's how we define the distance between a vertex and an edge. So using this new tool, we will get at most big O tilde 1 many pairs of x and y, and we will have to compare between them to get the minimum among them. And we for that comparing, the query time will be big O tilde 1. And so space required for one fault, let us discuss about that. So we have stored we have used big O tilde n square many maximizers, and we need to store them. And for that maximizers, so we should take we have to store the path also, and the fault which is maximizing the fault set, which is maximizing the distance. So this all those maximizers, all those things should take constant or polylog n many space, and for that we store paths in decomposed form, which I am not getting into details. Decomposed form just stores it in some nice way to get the space required. So for a fixed f, decomposed form will take only constant many space. And this way we can just take the space will be big O tilde n square for one fault. So this way we solve the problem for one faults, and using that one fault tolerant distance oracle, we can create for f equal to 2. And so we recursively increase this number of faults, and we can create for any general number of faults. And this will take for a fixed particular for a fixed if the size of the oracle will be big O tilde n square and query time will be big O tilde 1. So thank you for your time. I hope I was able to convey my results. Thanks.